So we started off the year with log functions, then exponential functions. Now we're going to add to our suite of functions with the trig functions, which of course we already know what the trig functions are, but we also now want to know how to differentiate them and integrate them and all that sort of stuff. So it's just going to give us a whole heap of functions that we can use in solving problems. But before we get to that, a reminder about Radian measure. Okay. Now we did talk about it last year, so we were able to do the questions in the exercise. But now in year 12, Radian measure is the standard measure when it comes to trig and calculus, basically. Because in order for the calculus to work, the angle measure has to be in radians. More about that when we start looking at differentiating. So the conversion, you may or may not remember, the way I think of it is a complete circle is 360 degrees. The circumference of a circle is 2 pi r, so I can easily associate 2 pi with 360. I mean, obviously it's actually pi is 180, but that's just the way my mind works. Yes, I know it's weird. Arcs and sectors that we start off with. We know how to find the circumference of a circle. We know how to find the area of a circle. But what if we're just interested in a piece of it? Now, if I'm only interested in the distance from A to B, then we know, AB is an arc, technical term. If I want to find the length of that arc, it's going to be that fraction of the circle. Now the advantage of using radians here is something nice happens. Because instead of saying that angle divided by 360 is the ratio, if I'm talking about radians, I say that angle divided by 2 pi, the 2 pi cancels in the 2 pi r of the circumference, and you get a lovely neat little formula. Length is simply the radius times the angle size. But again, in order for that formula to work, the angle must be measured in radians. What happens with our sector? Again, if we just use that fraction of a circle, well, it doesn't all cancel this time. The pi's will cancel that, and we get a neat little formula, a half r squared theta. So that's how we can find the area of just a sector of a circle. So let's do this one. Now I've deliberately written 45 degrees there, just once again to highlight, no, got to be in radians. So to use this formula correctly, r theta is not 45 degrees, but pi on 4 radians. And so we get an exact length of 5 pi on 4, which would approximately be whatever 5 times 3.14, and the area of our sector, again, I've got to use pi on 4, not 45 degrees. And there's the exact value, 25 pi on 8. So 25 on 8 times 3.141. Another thing we often like to find is the area of the minor segment rather than the sector. So just that little piece there. Well, it's simply, well, some say simple, depends I suppose on the numbers, but it can be easily worked out by getting the area of the sector that we've already found and subtract the area of the triangle. And so that's what we basically do. So if I want to create a formula, there's the area of the sector, half r squared theta, and the triangle, I'll use my sine rule for the triangle, half AB sine C, which in this case would be a half r times r sine of theta. And so if I substitute into that one, there we go. And you probably guessed that answer anyway. Yeah, it's 25 pi root 2 minus 100 all divided by 8 root 2 centimetres squared. This is where science teachers now go, because they can't cope with exact numbers. They love their approximations. All right, 14b. Yes.